Welcome, student. Today I am going to discuss the new topic of this unit one, turning moment diagram. It is very important topic and it is very essential for this semester in this subject and as well as for important examination for your future. Now, the topic name is turning moment diagram for a single cylinder double acting steam engine, turning moment diagram for a four stroke cycle internal combustion engine, turning moment diagram for a multi-cylinder engine, and last topic is in this video fluctuation of energy. Okay, so let's start. What is turning moment diagram? Turning moment diagram, it is a basically graphical representation for the turning moment and the crank angle. We also know that when we derive an expression for the turning moment या crank pin effort, that is equals to FPR sin theta plus sin to theta upon 2 root n square minus sin square theta. Okay, when we are going to draw TMD, then we represent theta on x-axis and turning moment on y-axis. So here I mentioned that it is plotted on Cartesian coordinate in which turning moment is taken as the ordinate and the crank angle as epsilon. Now, the value of Fp we also known as piston effort small r, radius of crank small n, ratio of the connecting rod and radius of crank theta, angle turned by the crank from IDC. From the above expression, we can also see that the turning moment is zero when the crank angle is zero. So now if I am going to put the value of theta equals to 0 in this equation, then we got the value of turning moment equals to 0. You can see because sine 0 value of sine 0 is 0, sine 2 theta also 0. That's why the whole equation is converted to 0. Okay. Next, it is maximum when the crank angle is 90 degree. We can check again. If I am going to put the value of theta equals to 90, then we know that sin 90 equals to 1, then the value of turning moment on the crankshaft will be maximum. Next, and it is again 0 when angle is 180. If I am going to put the value of theta equals to pi or 180, then it becomes 0. So these all things we can represent on the graphical presentation between the turning moment and the crank angle in figure 1. Now we can see that in this diagram when the crank angle is 0, then it will lie on a O point, yeah, A point. When it is maximum when the angle is 90 degree, and it is again 0 when angle is 180, and again maximum when angle is 270, and again 0 when the angle is 360. Okay, now when we are going to calculate work done, then we study this diagram. We take mean resisting torque, mean resisting torque, the area under the rectangle. Which rectangle? Rectangle OAFE. OAFE, that is our required work. That is our required work. And the area above this curve, like BBC and DDE, these are the excessive work, because here we are going to calculate this work from the mean resisting torque line, that is AF. Okay, so now the curve CDE is the turning moment diagram for inner stroke, and similar to curve ABC, you can see CDE, this one, and similar to ABC, this one ABC, and this one CDE. Okay, now since the work done is the product of turning moment diagram, turning moment and the crank angle, because we also derive an expression T into theta, that is equivalent to work done per revolution. Since the pressure inside the cylinder, engine cylinder, is less than the atmospheric pressure, then we can see a negative work done. Okay, now I am going to discuss turning moment diagram for 4-stroke cycle internal combustion engine. We know that in an Otto cycle or diesel cycle there are 4 stroke. First is suction stroke, second one is compression, third one is expansion, and fourth one is exhaust. So during the suction, pressure inside the cylinder will be less than the atmospheric pressure. So here we got the negative curve, this one, during the suction. When we compress the fuel, then pressure inside the cylinder is also decreased. We can say that work done on the system, that means it will give the negative loop. Now when the pressure inside the cylinder will be increased during the expansion stroke, then the value pressure inside the cylinder will be more than the atmospheric pressure, then we achieve positive loop. Again in exhaust, yeah, exhaust, the pressure inside the cylinder will be reduced as compare atmospheric pressure, then we again achieve negative loop. So you can see in the theory, since the pressure inside the engine cylinder is less than the atmospheric pressure during the suction, then we achieve negative loop. During compression we also got higher negative loop. During expansion we also got positive loop, this one. During exhaust we again achieve negative loop, this one. So I hope you will understand how we can use turning moment diagram for 4-stroke cylinder engine. Now I am going to discuss turning moment diagram for a multi-cylinder engine. Firstly, we can see the TMD. We know that one revolution is equivalent to 360. This one revolution is equivalent to 360. If we are using multi-cylinder, then it is equivalent to one is 120 each. same 120 and same 120. So we can draw this curve 120, 240 and 360. So same procedure we are going to discuss in this topic. Now I am going to discuss fluctuation of energy. What is the fluctuation of energy? It is the basically it is the basically we can achieve from the turning moment diagram. Fluctuation of energy can be determined by the help of this diagram. We consider crank rotation. Firstly, we consider 0 to P, then P to Q, then Q to R, then R to S, then S to E. Okay, so suppose I am going to discuss 0 to P, yeah, O to P. Then we required work is OABP, and I am going to achieve only ABE. So here we got less energy. For next, if I am going to consider the triangle PBCQ, PBCQ, then the value is required energy is PBCQ, and I am achieving in this crank revolution PBBCQ.